with us before or after you actually hand in the piece of paper shouldn't be a huge deal. It's not like it's a huge advantage to meet with us before or something. So, all right. So, question, yeah. What's that? It's on the schedule. I think it's next Monday or Wednesday. Monday. Okay, so a week from today. So you guys should, meet with your team, start having a conversation about what you want to do. And again, it's not an absolutely binding contract. It's more just like you guys put some thoughts on paper and then we have a conversation about what would be a good project. All right. So let's. Last time, remember, we had this little kind of a side story about column stores, which is a different way of organizing a database system in contrast to the sort of conventional, more row-oriented design. So just to recap what that was about. I'm going to recap that quickly, and then we're going to kind of go back to our regularly scheduled program, which is walking through this internals diagram. So we've kind of gone through and talked about the executor, and we talked a little bit about access methods. Today we're going to talk about buffer management and memory management. And that's going to almost, then we just have one more lecture before we can finally really talk about how the query optimizer works. So we're going to, after this lecture, we'll talk about join algorithms. And then once we talk about join algorithms, we'll put it all together into a picture of what the query optimizer, or what a sort of standard design of a query optimizer would do. So today is buffer and memory management. Next time is joins, and then finally we'll get to optimization. All right, so just to recap the idea of column stores, just so that we all kind of remember what we did last time, and then as I said, we'll get back to talking about buffer management. So the idea with a column store is that, fundamentally by storing every column in a separate file, like a stock set of stock quotes like this, if we want to read some query that only accesses 3 columns, would only have to go read these 3 files from disk. So, it would save, say, 3/5 of the total I/O, right? And the key observation is that these analytic databases that do these kinds of big scans are not usually 5 columns big, but hundreds of columns big, and yet the queries might only access 3 or 5 or 7 of those columns. So you often have this kind of access pattern of very wide table access via queries that only look at a small subset of the column. So obviously we're going to get a huge reduction in the amount of I/O we do for these scan-intensive queries in this particular setting. Okay. So the kind of use case where we like columns are these so-called OLAP warehousing workloads. They're workloads where new batches of tuples arrive. We're not doing lots of little inserts one at a time that have to be handled transactionally. We can insert a big batch of stuff at a time. And we're running these queries that scan and aggregate a large set of stuff. So this is really the use case of some, say, retail organization wants to analyze their past history of sales transactions. They might dump a night's worth of sales transactions into this database every night, and then they do this big analysis that looks at how sales transactions have broken down by demographics or region or whatever it is over time. Okay, you can imagine this kind of workload occurs all over the place. The query is really these big scan and aggregate workloads. This is in contrast to these OLTP online transaction processing workloads, which are more like the things that are happening at the point of sale terminals or the ATMs, or when somebody puts something in their shopping cart on Amazon, where you have to do a little update of a single record. You have to insert a whole new record. Maybe you have to read the current balance of a bank account or the current set of items that are in a shopping cart. This happens for maybe thousands or tens of thousands of users concurrently. In that case, the OLTP case, you've got a sort of very write-intensive, lots of updates, and lots of operations on sort of single operations, single records at a time on behalf of many distinct concurrent users. Right, so this is kind of this column store idea really works well in the OLAP ID case, and as we said last time, it's not going to be a good choice in the OLTP case because updates are going to have to go right to the end of each one of these columns, and we're not going to get a big performance gain in that case. So in practice, though, this column store idea can get us, say, a 10x performance gain on real-world workloads. So we looked at some performance results last time, and then at the end of class last time, we just briefly touched on this idea of write performance and looking at how to make writes go fast. And we kind of laid out this design for what we call the write-optimized and read-optimized system. So the idea is there's this write-optimized database, there's a read-optimized database. We insert data into this write-optimized storage, and then the read-optimized system is this compressed, sorted thing that sits on disk. And there's this process called the tuple mover that kind of copies data out of the WAS and periodically writes it into this ROS.
Question?
Yep.
Can you just remind us what OLAP and OLP is?
Sure. Sorry if I didn't spell them out. OLAP is online analytics processing. And like, okay, so this word online is kind of confusing, right? Because you think online is like means, I don't know what you think online means, like logged in or something. I think the idea is it's interactive, like users show up in a terminal and type a query and expect to see an answer. That's what people mean by online here. Analytics is, of course, this super overloaded word, but in database speak, analytics means running scan-oriented aggregate queries. So if you hear a database person say, I'm doing analytics, that means I did a like select from group, select average group by something, right? It doesn't mean they ran some fancy machine learning algorithm on the data. And then OLTP is online transaction processing. And this is this use case of updating individual shop cards or bank account balances or something. Okay, anyway, so we saw this problem. One of the sort of observations we had was that write performance in these systems could be bad, so we might like some way to make write performance better. The reason write performance is bad is because if you're doing inserts to the ends of each one of these column files, you're going to do random I/O, many random I/Os to insert a single record. So our idea was to do this kind of batch thing, and in particular, this design where we have this write optimized store which buffers a bunch of inserts in memory, and then this tuple mover process which periodically copies data from this in-memory store into this compressed sorted thing, right? And then we talked a little bit about how this compressed sorted thing, the problem with even this design is that, well, if I load up a memory's worth of tuples, I might have to, do I have to rewrite this whole compressed sorted thing at the end of that process? That sounds like it would kind of suck, right? Because I got 10 terabytes of data on disk, and I have to like resort it and rewrite it out to disk every time I get a couple gigabytes worth of new data that gets inserted. We don't really want to do that. So the design that we kind of developed in the C-Store project is this kind of something that looks like this, where you take these write optimized stores and you just you compress them and sort them and write them directly out to disk without merging them into the existing read optimized structure. And then periodically in the background, you merge these read optimized things together to get sort of logarithmically larger things. And the idea with this kind of merging process is that it will result in some small number of these read optimized store objects on disk that we'll have to access to answer any one given query. But we won't have to do this rewrite the whole database thing, or at least we won't have to do it very often. We might do it once every 100 or 1,000 times we produce one of these new ROS objects, but we won't be doing it every time we produce a new ROS object. Does that kind of make sense? So this idea is sometimes called log structured merge trees in the sort of systems community. You can sort of see why it's log structured. These, you have logarithmically sort of exponentially larger ROS objects as you go further away in time as they get older and older. And you're sort of merging them together, and you can think of it as being arranged in sort of a tree-like structure. All right? So are there questions about C-Store? Okay. Just to sort of give you like a little bit of a recap, we developed this system C-Store at MIT starting in around 2005. The academic project had mostly wrapped up by 2008 or 2009. It was commercialized as a company called Vertigo, which HP acquired. So they're now using this to manage 5+ petabytes. And I think partly as a result of this work, all of the major vendors are now basically shipping something that claims to be a column-oriented system. So, all right, so just to recap, you can go look at the original website, which is a circa 2005 website, see some of the papers and other things there. Okay. All right, so let's kind of go back to our database internal story and start talking about what we do. Okay, so what is the buffer pool? You guys have all built a simple buffer pool. What's a buffer pool do? It's just a cache, right? A cache of recently used pages. Okay? And as you guys have seen in SimpleDB, it's kind of this convenient bottleneck that all of the accesses go through. Okay, so every time a transaction or a query reads a page, it'll ask the buffer pool for the page, and the buffer pool will make a decision about whether it has that page available. It'll sort of look in the whatever hash table structure that it has and say, yes, I have this page, or no, I don't. If it has the page, then it'll return it back to the user, and if it doesn't, then it'll fetch it from disk and give it to the user, right? And it turns out that this structure is going to be kind of nice, that every access goes through the buffer pool because, for example, it'll give us a way when we start implementing transactions and locking, we can associate some of those transactions and that transaction and lock information with the pages in the buffer pool. So we'll have sort of every access mediated by this data structure. All right, so we can think of the buffer pool just as being, conceptually, it's just a table, page ID, some metadata, like locks, etc., and then a pointer in memory, and then some for example, last access time or other information. Okay, so pages like page ID 1, page ID 2, we'll talk about what this lock information looks like when we get to talking about transactions. A pointer to some location in memory, maybe CD, and maybe last access time, like 23 p.m. Okay, so we might have some information about the last time somebody read or wrote or both a given page like that. Okay, so this thing is a cache. So, well, before we talk about this, about how we manage this cache, let's just talk a little bit about why a cache is important in a database system. So, why is a cache important? Why do we care about using this cache again, right? Yeah.
Well, it saves you a lot of time if there's certain pages that you access a lot more than others.
Okay, so like any, the common use of caches is there's this thing that we're repeatedly doing, which is reading these pages. Reading these pages from disk especially is really expensive because, as we've seen, it takes 10 milliseconds or something to go to a seat to read these things. So if you're repeatedly accessing these pages, you'd like to do it through a cache rather than going back down to disk. All right, and so that's the high level. It's actually worth thinking a little bit about what the use case for caching in these two different scenarios is. So in the OLAP case, if you think about what happens in a system like CStore, it's actually caching is probably less relevant here, right? We're doing these big scans of large tables that by and large don't fit into memory anyway, right? So we might be able to cache either some small tables in the case of doing joins or a part of tables. We're probably not going to have the whole table that's being scanned in memory in a system like CStore. In one of these OLTP systems, though, where we're doing lots of little lookups on behalf of, say, some number of concurrent customers, this caching is really going to be critically important, right? There's 10,000 people all coming to this bank account website, and they're all, once one person comes into the system, they're going to do a bunch of little transactions that involve updating a small set of records that belong to them, right? So you read your bank account balance, that gets displayed on a screen. Maybe you read whatever your account number. You read a whole bunch of individual pieces of data that get used to populate different screens, and maybe you update some of those things. So if you had to go do a disk I/O for every one of those 10,000 people every time they came into the system would just fall over because those would be random disk I/Os. You can't really predict who the next customer is going to be. There would be these random I/Os that are going to kill you. Right. So in this OLTP case, this caching is really critical. And it's so critical, in fact, that in the sort of most carefully designed OLTP systems, you try and size the memory of the database system, the server, such that the sort of active, at any given time, the number of active users or active pages in the system can fit in memory, right? Like if I have some number of concurrent users hitting my bank account website, and some large fraction of those users, and I can't fit all of the data for the pages that they're currently accessing in memory, it's going to be really bad because, I'm going to be kind of swapping through memory. I'm going to, one user is going to access a page, and then there's not going to be enough room, and so we'll evict some other user's data in order to make room for it, and then that other user will want to access something, there's not going to be room, and we'll evict data, and you'll end up with this kind of thrashing scenario. So in these OLTP workloads, this caching is really critical, and you want to sort of size the memory of the system so that the working set, this set of concurrent load kind of fits in memory. And we'll talk about in the paper that I signed for today, this DBMin paper, how they enforce this kind of working set fits in memory property, but generally this is something the system will do. Okay, so does everybody get why we care about this? It's super important. If you don't have it, these OLTP workloads are going to fall over disastrous performance. You'll go from tens of thousands of transactions a second to whatever the limit of disk is, tens or hundreds of transactions a second. Yeah? So there are lots of different things that people do. So one thing that people do is that sometimes if you know, like in these OLAP settings, if you know what kinds of queries people are going to be asking, of course you can pre-compute or partially pre-compute answers to those things. So there's lots of different techniques. We're going to talk probably the end of next week after we talk about optimization, a little bit of what are the kinds of things we can do in order to optimize these OLAP workloads. And yeah, one thing you might do is cache some pre-aggregated view of the data. There's lots of different techniques like this. Okay. All right, so this thing is a cache. So so what's the best cache eviction policy? Like, how should I manage this? Anytime there's a cache, right, you immediately say, what should I do? So what is your operating system do? Yeah, okay, so she said LRU. So it probably does something kind of like LRU. It uses one of these clock algorithms or something to maybe avoid actually storing a timestamp with every record, but it stores something that sort of approximates LRU on these pages. So is LRU always the right thing to use in a database system? We talked about this briefly before, but is it always the right thing to do to manage pages with LRU? Okay, so when would managing LRU be wrong? So does everybody know what LRU, least recently used, means? Okay, so least recently used would mean when you have to evict a page, you find the one that was that has the oldest last access time, and then you would evict that page, right?
Well, if you access a database or a table that is a little bit bigger than however much you can store, and it's something that you frequently access, then you can cache almost all of it, but then every time you want to access it again, you're gonna have to research for everything, because assuming it stores the last thing, it bumps out the first one, and then it's gonna have to go through them all again.
Yeah, so LRU, so one observation is that when you're doing repeated sequential scans of a table, LRU is, and the table doesn't fit in memory, LRU is actually the worst possible thing you could do. So let's just see an example of this. Suppose I have 3 pages of cache. So my memory, I can hold 3 pages of memory A, B, C, and I have 4 pages of, so this is memory, okay? And I have 4 pages that I'm reading. So I'm reading pages 1, 2, 3, 4, over and over and over again. In sequential order, I read 1, 2, 3, 4, 1, 2, dot, dot, dot. Okay, so let's see what happens. Well, if the first thing I do is I read page 1, it fits in memory, right? And then the second thing I do, so this is imagine this is time going down like this. Okay, then I read, page 2 and it fits into slot B. Then I read page 3 and it fits into slot C. And now I read page 4, right? And what happens? Well, the last recently used thing was page 1, right? So I would write, I'd evict this and I'd write 4 in, right? And then I'd have 2, 3. And now you can see what's going to happen. We're going to read 1 next. We're going to miss on 1. We're going to evict 2, right? So I'm never going to find what I should find in cache, right? So these are all misses. Okay, this is, every one of these accesses is misses on the cache. Okay? So what should I have done? What would be better than this?
The opposite.
Do the opposite, right? It's sort of confusing, but actually most recently used is the best thing to do in this case, right? So what would happen in most recently used is that I would have evicted 3 at this point, right? Because that was the most recently used page. And then the next thing I would have done would be to read 1, and I would have hit on 1, right? And then I would read 2, and I would hit on 2, and then I would read 3, and I would miss on 3 because I would have evicted it, right? And then, but then I would evict 1, right? And then I would hit on 4, and so on and so forth. So with this case, with MRU, we would hit on 2/3 of the accesses in this case. You guys see that? Okay. So MRU basically is the optimal thing to do in this particular case. Yeah, and that's a little bit counterintuitive, I think, but it's kind of key. Yep.
I mean, is there anything like looking at whatever table it is that you're doing a lookup on and seeing how many entries there are and saying like, don't cache more than...
Okay, good. So you didn't read the paper, but that's fine. So the paper today talks exactly about this idea, right? Which is that what we want to do is, you know, in general, we have this observation, which is that, you know, in this case, it would have been better to use MRU instead of LRU because, well, you know, we know how much memory, if we know how many pages of memory we have, and we know how big the table is, we can, you know, make a decision about whether we should use LRU or MRU, right? But there's lots of other things that we can observe, right? Like, the database system actually knows a lot about how it's going to access a table in the future. Right? Once we build a query plan, well, you know, if this sequential scan is, we're only doing one sequential scan of a table as a part of a query. I mean, you know, maybe we don't need to bother to cache it at all because we're just scanning through the thing once. And so why evict all the pages from memory if we're never going to re-access them as a part of this query, right? It's just scanning the table once. I shouldn't, you know, throw out all the other queries, you know, pages for all the rest of memory because, you know, I'm just wasting memory when I do that, right? So that's kind of what this paper talks about, this DBMin algorithm. Right, so let me just say, this case, you know, MRU is optimal for repeated scans. It's actually sort of the optimal period for repeated scans because if you think about the case where it does fit in memory, it doesn't matter actually. MRU works just as well as LRU when the whole relation fits in memory. And when it doesn't fit in memory, MRU is the best thing to do. So,
Would it be more optimal to just put 1, 2, 3, and every time you get 4, just go read 4 from disk?
Sure. So you could have something like that that just has like a fixed, and maybe that's it's no more or less optimal, right? I mean, actually, MRU is going to hit just as frequently as that algorithm will. But you know, maybe it's easier or simpler to think about it doing like this. Like you just say, you know, this part of the file is always going to be missed on, and this part of the file is always going to be, you know, we're always going to hit for this range of the file. That would be equally as good, probably in this simplified example. Okay. All right. So this paper that we assigned is this DBMin out paper, and basically it proposes this collection of algorithms for talking about how to manage cache. Starting from this observation that different instances of different occurrences of different sort of accesses to a file should be governed with different page management strategies. Okay. So it, in particular, says two things. One is that there's a per file instance. I'll explain what I mean by that in a second. Buffer pool. And then two is a different eviction policy per buffer. Okay, so rather than having one global buffer pool, what we say in this DBMin algorithm is that for each time a query accesses a file, so for any file that's being accessed by any query, for each instance of an access like this, we'll allocate a little, you know, a collection of pages for that specific file access. Okay, and the number of pages DBMin tells us how many pages we should allocate for each such access. So if I have query 1 reading table A with a, you know, a sequential scan, I'll allocate so many pages. If I have query 1 reading table A through some index or something, I'll have a different set of pages. If I have some other query that you know, reads table B through a sequential scan, I'll allocate a certain number of pages for that, and so on and so forth. Right? So each time a table gets accessed by a query, we'll allocate a little buffer pool for that access time. So that's what this first statement means. And then the eviction policy that we use for each one of these buffer pools is going to depend on the type of access that we're performing. All right? Okay. So, and it's really, I mean, the algorithm itself is not, I mean, it's hardly even an algorithm. It's not very complicated. Basically, the paper just sort of lays out these observations about what types of access we typically perform in these databases, okay, in databases. So, just write out database access. And so if I give you, think about even what we've learned so far in class. If I give you a file, a heap file, what are some different ways that the sort of query algorithms that the query operators we've seen so far might traverse through the pages of a file? Well, we know one, right, which is a sequential scan, right? So that's one way we might traverse through it. But the paper says, well, there's some, we want to be a little bit more, think a little bit more about the types of accesses. So if you think about a sequential scan, like a nested loops join, and you think about whether a relation, a heap file is on the inner or the outer of a nested loops join. So what do we know about the type of the sequential scan that we're doing if a file is on the outer of a nested loops join? From the point of view of the buffer manager, the relevant point is we're only going to scan it once, right? So we're going to do, when it's on the outer of that loop, we're only going to scan through it once. So from the point of view of this, sort of file, like a given file instance, right? Like a given operator, like a nested loops join, right? That operator only needs to access given the file that's on its outer, a single time, okay? So they call this a straight sequential scan, okay? Which means, as opposed to when it's on the inner, right, in which case we're going to re-access it over and over. So we're going to loop over and over again, right? So we have straight versus looping. Okay? So that's one type of access pattern. What's another type of access pattern that we've seen that we might imagine? Well, what's the other main access method we studied? We studied sequential scans, and what's the other one? It's a tree structured index thing, right? Okay, so, and from the point of view of a tree structured index thing, there's actually two kinds of it actually is sort of two access patterns if you think about it. There's the access pattern of traversing down the pages of the tree, the internal pages of the tree to find a record, right? And then there's the following the pointers at the end of the record, right? So remember the way these things work is we've got a heap file like this, we've got our index, which has these pages hanging off of it. Tree like this, right? And these pointers, these pages have pointers into, this thing. And those pointers kind of go all over the place in this thing, unless this file happens to be clustered according to the index. Okay, so this actually suggests two other kinds of access methods that we might encounter. So if you want to tell us what they are, or access patterns, sorry. So what's the access pattern when we're traversing down an index? What's different about traversing down an index than doing a scan of a heap file? Think about doing multiple index loops over and over, like by putting index at the inner of a nested loop. Yeah?
The root of the tree has temporal locality.
Okay, so we're going to re-access the root a whole heck of a lot more than we're going to re-access the leaves, right? In fact, the root is going to be accessed every time, right? And then the level below that is going to be accessed. The probability that a page, if you think about random lookups in this thing, the probability that a page at the second level gets accessed is exponentially higher than the probability that a page at the next level, and so on and so forth, right? So it's probably, if you model the workload as a completely random set of lookups, it's probably going to be better, all things considered, to cache the top levels of the tree than the bottom levels of the tree, right? It's much more important to hit on the top levels of the tree than on the bottom, okay? So we can also talk about hierarchical lookups. And again, we can talk about straight versus looping. one-off index lookup versus, knowing we're going to repeatedly re-access this thing over. Okay, and now what about this case, these lookups in the heap file? What is that access pattern like? Yeah?
I just want to ask a question about too.
Yeah?
So I just don't understand something, because if all the data is stored in leaves, why are we accessing like wells above the leaves?
Because we have to, when we traverse down this, like imagine I look up, employee ID 1, and then employee 27, and then employee ID 22. Every time I look up that employee, this index structure itself is a collection of pages, right? And those pages, may be in memory or they may be on disk, right? We're not required that the pages of the B tree all fit into memory, right? So the pages themselves, the index pages that index the data, can be stored on disk. You look confused still.
Yeah, why wouldn't we just read from leaf to leaf instead of next?
Well, you can sequentially scan the leaves, but remember, we're not talking about using this index for a sequential scan, right? We're talking about, we've got a whole bunch of, imagine 1,000 users all concurrently accessing the system at the same time through the same B tree. Like they come into your bank account and you have to look them up by, account ID, right? So you have a whole bunch of lookups you're doing by account ID, but those account IDs aren't, sequential in order and not done in order, right? They're just different account lookups on behalf of different users. And so each one of those things, it wouldn't make sense to scan through the leaves to do this, right? Because if you scan through the leaves, you're effectively scanning the whole database. You're much better to do those lookups as, doing 3 or 4 IOs to traverse down the B tree to find the record that corresponds to that account ID. Cool? Okay, all right, so now what about this sort of access pattern? You think about traversing along the leaves, for example, of a B tree, when the B tree is unclustered. What kind of access pattern do we see in the B file in that case? Yeah? Yeah, so we're going to see sort of this random, like just jumping all over the place in this thing, right? Okay, and again, of course, we can, this random, we can sort of talk about looping with random, but it's not, we can talk about straight versus looping, I guess. Okay, so, and the paper has some other, types of accesses that arise when these B trees are clustered, but to a first approximation, these are the kinds of relevant things that we need to think about. Okay, so now let's write out these. Write out just some abbreviations. So let's call sequential scan straight SS. Let's call this straight looping SL. LS. Okay, let's call hierarchical. SH for straight hierarchical, looping hierarchical, straight random, and looping random. Okay, so imagine these are our 6 access patterns that we can have. So now let's think a little bit about how much memory and which eviction policy we should allocate to each one of these things. Okay, so we've got straight sequential, straight looping, straight hierarchical, looping hierarchical, straight random, looping random. Okay, and so the question is, how many pages? And what? Okay. So if I'm doing straight sequential access, how much memory should I allocate to that? I said, right? Just like 0 or 1 page or something. I have 1 page that I need because I need to keep the current page I'm scanning. Okay? And so it doesn't really matter what policy we use, right? Okay, so, and then straight looping. So what do we want to do with straight looping? What's that? Okay, so we said we want to use MRU, and how many pages should I allocate? Yeah? Yeah, well, remember, so right now we're just talking about access to one table, right? You're right that for the join, we would ultimately like to allocate, if we're doing a join, that's what we'd like to do is 1 plus the size of the smaller table, that's the number of pages we'd allocate. But if you think about, so in the straight looping, sort of what I mean here is this is one file, like either the inner or the outer that's being iterated over and over and over again. So we'd like to allocate the number of pages that we have of the, so the size of the table pages, right? Or, right, the problem, of course, is that this table might be really big, right? So then in that case, we have this, so we kind of have to decide, like, how many pages can we really spare to manage this thing? So, like, or, as much as possible, right? And the paper doesn't really go into the details of how you figure out how you should decide, how many pages you're willing to allocate to this kind of buffering. For now, you can sort of think of it as as much memory as you have, you want to dedicate to this particular thing. Okay, so we can kind of go through this, right? These straight algorithms, because you're just accessing, one page at a time, it never really makes sense with straight anything to cache more than one page, right? If you, okay, but now let's consider this case in particular of looping hierarchical. So what should we do in the looping hierarchical case? Intuitively, like what would you do? Well, you want to do, again, something like we already said, right? You want to preferentially cache the top levels of this tree, right? So you sort of want to, as much as possible, but, you want to cache as much as possible, but if the whole thing won't fit in memory, then you should make sure when you have to evict something from this, you evict leaf pages, not top-level pages, right? Because evicting top-level pages is going to kill you. Right, so the policy here is this, like, evict leaves first. Okay, and for these other ones, it doesn't really matter what page management scheme you use, but this, because we're preferentially caching top levels, we're going to, evict so the total number of pages we want, again, I guess I should say, sort of as much as possible. But the eviction policy is to evict the leaves of the tree first. Okay, and then looping random, again, it's not really very much different than this sort of straight looping. If you're looping over a small set of random records that all fit in memory, then you just want to cache all that, the size of that loop. If you're looping over a set of records that don't fit in memory, you want to use MRU or something on them. So it's very similar, in fact, to this like. Sorry. Okay, so so now this sort of gives us the design, right? Basically what's going to happen is that when we allocate when we start running a query, we're going to allocate memory for that query using this kind of table. How are we going to know what memory we should allocate? Well, we're going to sort of analyze the different access methods in the query, and we're going to use based on the access methods that are employed in the query, we'll instantiate the appropriate number of pages of the appropriate scheme. Yep. Yeah, so this is an interesting idea, and it's one that maybe we'll come back to when we talk about in memory. And people have recently thought about building database systems that are optimized for given this sort of assumption that OLTP workloads really ought to fit in memory, maybe this idea of thinking about managing the database as a collection of disk pages isn't quite the right thing. And instead, we should think about this as managing the database as a collection of records, and then kind of spilling the records that we're not accessing very frequently back, to disk, and reorganizing them into pages in some way or something, right? More like maybe the way that virtual memory systems work, right? right? So I think that's an interesting suggestion, and it's one that we can talk about more when that comes. So another question? Okay, so let's take a break and we'll come back. I want to do a little demo of this PGAdmin tool, and then we'll just talk a little bit more about how we would really implement a system around this idea, and some more about some of the sort of issues with memory management and databases. Okay, so come back in, I don't know, when that says 3:20. That's just, I mean, I don't know. You said you yeah, you would always get. Maybe I misspoke. I think it should be the same. I might have misspoken. That's an interesting. It's an interesting question. I mean, I don't know. I did write down.
Yeah. Well, I think. I think it has to do with.
Oh, I didn't remember what it was.
It might be something like like n minus over n over space.
I see what you're saying. Okay, you're right.
I'm just wondering because I think that'd be that's easier.
It's super easy. I mean, the only thing you have to do is like right now it's we don't really have this buffer pool, right? So the buffer pool is whereas in order to implement this, you have to so we're going to talk about how when you stage it, you have this stage. Oh, you're the one on tape. So, let's try something. I wonder if this is okay, if you directly type that actually put that no, this is your
Yeah, okay. So it has to be the first thing that you do it.
I think you have space. Well, okay, at least it was easy to solve. So you have space in front of the user. It worked?
Yeah, it worked.
Okay, all right, guys. So I just wanted to, before you guys, I don't know how many of you had started working on problem set 2, but one of the things that was that a laugh because nobody started working on problem set 2? One of the things that we mentioned in homework is this PGAdmin tool, which is kind of just a nice way to play with query plans, and you might find it to be useful. So I'm just going to show you a very quick example. This is the same example we looked at before, this employees, kids, and departments table. Sorry about the terrible formatting. So you have some query like this that finds all the employees with more than 7 kids who make more than some amount of money, right? So if we take this, and unfortunately this tool doesn't let me resize the font, but if you install PGAdmin and then you set it up, you can connect it up. You can add a connection to our Mimic database, or in this case, I've added a connection to this the example database that I'm using here called this lectures database. And you can click on the schemas and drill down on them and actually see what the tables are. There's the departments table, employees table, kids table. You can browse these things and see some. It's being very slow. The kids table is huge. You can browse the tables and see what you see. It's going to crash the computer if I should have done that. Anyway, so then if you come over here and you look at the, you can type a query in like this, and then if you click on this little, well, it can do a couple of different things for you, but if you click on this explain query button, it will actually generate this really nice looking diagram like this for you. We've asked you to draw these diagrams, and we're okay with you copying these diagrams out of this PGAdmin tool, or using these to guide your drawing or whatever. It doesn't need to be the asking you to draw the diagrams is not meant to be an exercise in doing something totally tedious. So you can look at this, and it's also just a nice way to understand what's going on. You can really see that in this case, it's doing a sequential scan. That's what this little icon means of this kids table, and it's doing a hash join of that with a hash table that it built by doing an index scan on the employees table. So the Sal index scan of the employees table, it builds a hash table on that, and then it joins that with the kids table using this sequential scan. And then it joins that with the hash table, a hash table that it built on the departments table, and then finally does a sort, and then a group by. Okay, so it's just kind of a cool way to take this, because otherwise you'd be parsing this explain output, which can be a little bit hard to understand sometimes if you stare at it. So you can just, sometimes it's nice to have this graphical representation, and you can maybe understand a little better what it's showing. You're probably still going to have to learn what this explain output is really showing to do the problem set, but hopefully this will simplify your life a little. Okay, so this is the tool is called PGAdmin 3, and it's just like a free thing that Postgres guys give away. So it's kind of a nice thing that maybe will help you. So there you go. That's my 1 minute advertisement. I think I'm done. Okay, so what we're going to do now is kind of come back to this page management idea and think a little bit about what would be required to build the system around this, and then we'll talk about some other memory management issues that arise in database systems that aren't really necessarily covered in the paper. All right, so okay, so the first thing to realize about this per file instance of the buffer pool is that unlike the kind of buffer pool design that you guys are doing in SimpleDB, where you have this one giant hash table that stores all the pages, in this setting, right, we're going to actually have now a little hash table per file instance, right? So every time we are accessing a particular file as a part of a particular query, we'll allocate a hash table for it that will store the pages. So we'll allocate one of these structures, one of these buffer pool structures, but on a kind of per query basis, right? So we have one. This might be for query one file file A, right? It might have a one-page buffer, right? And then query two file B, might have a different buffer, and then query two file A might have a different buffer. Okay, so in this case, maybe we allocate only one record because we're doing a straight sequential access. Maybe we're doing looping sequential on these two things. Okay, so the number of pages we allocate is based on the size of the file and the type of access that a given query is doing to that file. Okay.
You have a rate. You have an update that you can't have this file.
Yeah, okay. So now if you look at this, you should immediately start to think geez, how is this actually going to work, right? Because I've got this table where I got pages for A, that, you know, it seems like I've got two hash tables for A and maybe we've got the same pages, and how do we keep these things up to date, right? So actually what the paper proposes is this, that there's an additional kind of global hash table, right, that stores all the pages in it. So there's, this is the hash table that, like, we have, just like what you have in SimpleDB, except for that instead of these being pointers to disk, they're pointers up into these data structures. Okay. And then when you want to do a lookup, when you want to look up a given page, you look it up in this big hash table, and then, you know, go follow the pointers to read whichever, you know, record you actually want to find. Okay. And then when you want to do an insertion, you check and see whether the page already exists via the insertion. And so if somebody else is caching the page that you're about to try to access, you don't recache that page. You just rely on the cache copy that somebody else had, right? So this kind of case is like, so specifically what we say is same page access. So this is the case of the same page accessed by multiple queries. And the challenge is, so there's a couple of cases. One is, you know, you already have it, you're accessing a page, you go to access it, you know, you already have it locally. So this is like, you know, query 1 tries to access, query 2, you know, tries to re-access this page, it finds that it already has it, cached by itself, so good. Okay, you don't have to do anything. Query 2 is that you, is it's in the buffer pool. Case 2 is it's in the buffer pool and, you know, not owned locally. And then there are two subcases, you know, someone else owns it. So in this case, we did nothing. If somebody else has it, we're actually going to do nothing too. So, you know, maybe this page, this guy goes to access, you know, some next page of query 2, and it happens to be this one that query 1 already had in its buffer pool. We're just going to let that other guy own it. We're not going to doubly cache this. That would be wasteful. So we do nothing. Okay. And then there's this case where a given page it's possible actually for there to be pages in this heap file down, in this hash file down here that don't belong to any currently run query. For example, if query 2 terminates, right, there's no real reason to evict all the pages that query 2 had stored in the buffer pool as a result of it terminating, right? We're just going to leave them there. But we want to make sure that we sort of mark them as being reusable by some future query that comes in. But in the meantime, if somebody wants to re-access one of those pages, well, okay, fair enough. They should be allowed to do it. So if no one owns it, then we take ownership. Okay? Okay, and then the third case is it's not in the buffer pool. In which case we evict one of our local pages to make it. Okay? So in this way we can kind of build a system around this idea. It's a little bit complicated. I mean, if you imagine implementing this, you have to think kind of carefully about how you get all the details right to make this work, right? But I think you can kind of see how it would go. Yep?
If it's not in the buffer pool and you evict your local page, do you also evict it from the global table? Or do you just evict it?
So it wasn't in the buffer pool, so you're going to put it in the global table. Right? You're saying when you evict it, what do you do? Yeah, you better evict it from the global table as well when you evict it. And this can lead to some kind of weird behavior, right? Like query 1 is here and it's doing its great sequential and it's leading in pages and evicting them. And this guy over here is, you know, reading the same set of pages but in this looping hierarchical way. And so, you know, it's a little, there's some kind of funky contention going on where maybe this guy is evicting pages that this guy's later going to need. I don't really know how that works out. So. Okay. All right. So the paper. This is a pretty cool paper. I really like the performance study in this paper. They one of the things they did. This is one of the first instances that I know of people doing this kind of these guys in Wisconsin actually who did this performance analysis, Dave DeWitt, there was a group of people there during the 80s and 90s who really pioneered this style of performance analysis. So what they do is they generate a workload, like they look at, because they wanted to evaluate all these different eviction policies, like tens or hundreds of different policies and strategies for managing pages, but they didn't want to rerun the systems over and over and over again because it'd be hard to get reproducible results because like the different pages are going to be accessed at different times and memory's going to be different. So they did this what I call sort of profile-driven performance analysis where they benchmarked the system once, measured got a trace of all the pages that any of the queries that were running in the system ever need to access, and then they did this simulation study where they replayed that real-world trace over and over again and sort of enabled to sort of evaluate the hit rates of different buffer pool strategies under different sizes of memory and other things like that. So it's a cool performance study and a kind of a cool way to think about doing performance benchmarking in this case where you have a really, sort of lots of concurrent stuff that's all interacting with each other in very complex ways where running a real query might be, a real system might be kind of. All right, so the bottom line of the experiments is that they show that this gets you about a 3x speed up over just using LRU on some set of workloads that they thought was representative of what real database systems, transactional database systems at the time did. Interestingly, though, if you look at their performance results, they're maybe a little bit less good than this makes it sound. And the reason for this is that they did something which turns out to be a really good idea. Which is that, well, maybe let's see if we can figure out what you would like to do with a system like this. So you notice when we were talking about deciding how many pages to allocate to each of these different access methods, we said stuff like, well, looping sequential, we should allocate as many pages as we have memory for, right? And the paper is a little bit silent about exactly how many pages that should be. But they, one of the things that they said is that if there's not room for a given, to allocate pages for a given query when that query enters into the system, that they're going to block that query from executing until enough pages become free for that query to run. Okay, so this is sometimes called admission control. So we don't want to let these other queries run simultaneously with us because they're going to gobble up, they're going to try and use up some of the pages as well. And the more sort of queries that are running, every query that's running needs some minimal number of pages allocated to it. And the more queries that are running sequentially, concurrently, the sort of more pressure there's going to be on the buffer pool. And the more we're going to be doing random I/O and evictions and other junk like that, that's going to slow down the throughput of the system. Right? So we sort of want to run as many queries as we can in parallel, and no more than that, right? Where as many as we can in parallel is like the number that fit into the working set of memory. So it comes back to this OLTP idea we had at the beginning. We don't want to run too many queries in parallel because then we'll start seeing lots and lots and lots of evictions. And this paper, after developing all this mechanism, says that, actually, if you just implement admission control without any of this other stuff, and then you just use an LRU policy, you get something like 60% of that 3x gain, right? So 60% of that 3x gain is simply due to this admission control, right? That you just don't let too many queries run concurrently in the system, okay? And this is like a classic theme of distributed systems. Like, it's better to limit the number of things you're trying to do concurrently than to run too many things at once. And all major servers, database servers, and web servers and other things implement this kind of an idea because you have too many things happening concurrently, you just get tons of contention for resources, and the system will just fall over. Okay? All right. So, okay. So that's what I have to say about DBMin. One question that gets asked a lot in common is like, does anybody actually use this in practice? And from asking around, my understanding is that none of the major systems currently implement this DBMin idea. And I'm not exactly sure why that is. It could be because of this complexity. It could be because people have concluded that this extra 40% that you might get, and it's probably actually less than this 40% or whatever 40% of 3x is. It's less than that because if you use some simple heuristics like not caching things, sequential scans that are not going to be reaccessed. You can probably get close to as good as that 3x scan. Anyway, people don't use this in practice. What people use in practice, one thing people use in practice is what's known as love-hate hints. Okay, and this is a super simple idea. It just says, when I access a page, I tell the buffer pool whether I love this page or whether I hate it. Okay? If I hate a page, it means I'm not going to reaccess it again. And if I love it, it means I'm going to come back to this page and read it again because I love it so much, right? So, and you can see why this is a much simpler idea, because now I just need this one bit attached, or 1 bit per query for attached to each page. It tells me whether a given page is currently loved or hated, right? And if a page is loved, then I shouldn't. I just will evict hated pages before I evict loved pages, and that'll get a lot of the gain, because like this, I just won't love straight pages that I'm accessing through in a single pass, like a straight sequential page. I don't love those pages. And so I'm going to evict those pages preferentially over these pages that I'm going to access in this looping way, right? So you can get a lot of the benefit out of this kind of love-hate hints. Other things that people do are to, basically have just 2 buffer pools. One buffer pool that's like the, pages that have been only accessed once. And then when a page gets accessed again, it gets promoted up to a second, buffer pool of pages that are, the good pages, the pages we love. And then you evict pages preferentially from the lower tier buffer pool before you start evicting from the higher tier buffer pool. And you can see that this captures the same kind of intuition where, pages that aren't reaccessed frequently will just kind of be evicted. And so you can get some of these benefits without, having so much explicit modeling. But it would be a cool course project actually to look at, how much these different techniques matter in practice in a real system like Simple DB, for example, because there's lots of different schemes like this you can come up with, and I don't know that anybody's really systematically studied that. Okay, any questions? Okay, so let's talk for just a little bit about some other aspects of memory management in database systems. So this sort of, making sure that we don't do a ton of random IOs as a result of misses on the buffer pool, that's one important scheme. But there are other things that you would like to make sure that the database system, there are other ways that we can improve the kind of performance of the database system. So in particular, one thing we might like to do is to ensure that, to try and further avoid kind of random I/O as we read or flush pages. Okay, so think, for example, about the case of evicting a page from a buffer pool, right? If this page is dirty, if it's been modified and we're writing it back, then we're going to have to go to disk, and when we write it back, we're going to take a random I/O in order to do that right then, right? And so that might actually be it could become a pretty big performance bottleneck, because we'll be doing lots of write-backs of these random pages every time we, so we're going to be doing, a whole bunch of, incurring a whole bunch of page misses to do these write-backs of dirty pages. Okay, so other. Okay, so the first problem we said is random write-backs. So what might I like to do? What can I do to avoid this random write-backs problem? What's that? Did you say batch? So what would batch mean? Yeah, so people do a lot of tricks like this. Different systems have, if you go read about how these different systems work, there are many, many heuristics that people have proposed for doing this. But the basic idea is we're going to set aside a little bit of memory, which is going to be like our write-back buffer, like pages that need to get flushed back to disk. Okay, and one thing to realize is that dirty pages, can kind of be flushed back to disk whether we are evicting those pages from cache or not. Like the fact that a page is dirty in memory has been modified by some transaction. Whether it needs to stay in cache or not is sort of separate from whether or not it is dirty in memory. And as we'll talk about when we talk about transactions, typically in transaction system design, we're going to actually allow dirty pages to be written back to disk. Pages that haven't, are part of some uncommitted transaction to be written back to disk. Okay, so what systems will often do is just have some, separate side buffer that they are, scanning through. It's sorted in disk order that they're scanning through to just do writebacks. Okay, so a sequential writeback. Okay, it actually turns out that on modern systems, you can sort of get the operating system to do this for you for free, because you guys probably know the operating system itself has a page cache, a cache of data that's been read in, and so from files. So if you do a write to a file in Linux, like if you do fwrite to or write to a file, it doesn't actually go write those bytes to disk right away. Right? It doesn't bother to write the bytes to disk until either you force it to with this fsync operation, or it sort of decides that it's time to write them back because it needs to free up space in its own memory. And so the operating system is already doing these kinds of optimizations to sequentially write back pages, dirty pages. And so you can kind of get the operating system to do this for you. And you may have to call this fsync operation periodically, like at certain well-defined points, in order to enforce you get the transactional properties you need. But again, you can sort of imagine that maybe the OS can do this for you. So Postgres actually employs this trick. Although if you go read about how Postgres works, people complain about this fsync thing, causes this massive flood of I/O to happen at the moment you do the fsync, and the whole system becomes locked up and no transactions can run while this is happening. So there are lots of trade-offs. But anyway, so random writebacks is like one thing we might want to do, and so we can use a sequential writeback. Another thing we might like to do is when we're reading, right? If we know that we're in this sequential, we're reading a file sequentially, what maybe should we do when we're reading a file sequentially? Again, this is kind of an obvious trick, but what's that? Yeah, we're bigger than single disk pages, right? Like if I'm reading, if I know that I'm sequentially scanning a file, I'd like to, continue to let the disk sequentially scan that file instead of letting other random IOs that might be pending kind of come in the middle of that sequential scan, right? Because if I go do some other random IO, then I, take this, 2 seeks to go seek through the other thing, read, and then seek back to my sequential file and keep reading. So I ought to try and read in big sequential chunks when I know I'm scanning just sequentially. Okay, so this is like a sequential read. And then, the third thing is a kind of a trick we've already talked about, but when you're doing index scans, right? This, if you remember, this sort of random. In the case where you're doing this, like, random iteration through a bunch of pages of this index, right? Well, I know I'm doing a scan of a range of pages. I should sort those pages and then read them sequentially. Okay, so sort index page, sort index lookups in okay, so these are all really about getting sequential access. Going from random IOs to this world where we do all of our IOs as sequentially as possible. Okay, and again, without these kinds of tricks, your database system will just fall over. These things aren't, by and large, implemented in SimpleDB. The operating system will do some of them for you, like these sequential writebacks. But one reason why these are things that real systems have to think hard about, and they're quite tricky and complicated. Any questions about this? Yeah.
So these are less relevant for Flash.
Yeah, okay, so there's an interesting question about what does Flash change, right? So Flash has this kind of surprising property that so the answer to this is a little bit complicated but Flash has, the most relevant property of Flash is that random reads are not really very much more expensive than sequential reads. It's like, maybe a factor of 2, but it's not a 4 orders of magnitude or whatever it is with disks, right? So doing a bunch of random reads isn't necessarily as bad. So in particular, this third optimization probably doesn't buy you nearly as much in the Flash case. The interesting and complicated thing to reason about with Flash is that random writes are a killer on Flash. To the point that all the flash drive manufacturers implement this thing they call this flash translation layer that translates your random writes into sequential writes using a log structure. If you guys remember from 6.0.3.3, this is kind of the log structured file system. So this allows them to convert sequential writes, random writes into sequential writes. And it has the side effect that it converts sequential reads into random reads. But because random reads aren't really that painful in the Flash world, this is a trade-off that's considered to be okay. Because random writes in Flash are like, they're terrible. Like a random, you have to basically erase. We have these things they call erase blocks, and if you have to erase an erase block, it takes like hundreds of milliseconds to erase an erase block. And, you don't exactly have to do one erase per write, but you have to do one erase for every small number of writes. So these random writebacks probably might be able to get this sort of for free because of this Flash translation layer if you're going through it. But, in some ways, the Flash translation layer is then kind of working at odds with things the database system itself is trying to do. And it's a little bit interesting, actually, to think about how you should design the very lowest levels of architecture of the database system for this kind of for Flash drives. Okay. So maybe we'll just let's say a couple of last words about the relationship between the database management system and the operating system. Okay, so there's a long, as you can probably tell, or maybe guess, there's been a long-standing OS versus DB kind of debate. I mean, this has been going on since people very first started building database systems, to the point that when you built a database system 20 years ago, you would generally implement it without an operating system. Like the database system itself would take over the whole computer, and it would not have an OS there because you didn't trust that the OS could do anything right? And of course, that's not the way that these systems by and large work these days. But there still are some issues where the operating system, the semantics of what the operating system wants, or the behavior of the operating system doesn't necessarily align super well with the database. Okay, so some examples of this are double buffering in cache. And so we just talked about this cache management strategy where the database system thinks it knows what pages should be in cache, right? But the operating system is going to be caching some stuff too underneath you. And like, you're the database system, I know that I'm never going to access this page again. Why are you keeping it in memory, right? And so operating systems have now started to add some hints. Recent versions of Linux have an ability to kind of hint to say, I'm not going to access this again. But for a long time, this was could be a problem. The other kind of issue you often have is this failure to write back. So operating systems for a long time had no way to say, really put this page on disk, I really want it on disk. They would cache stuff in memory, but you couldn't tell them, like, no, I really want this page to be on disk. And it turns out that this page that really ought to be on disk is something the database system is important to database systems because it's how we commit transactions. We'll talk about this more later. But OSs, even sometimes, for a long time, they had this behavior where there were certain corner cases where even when you call fsync, this thing that claimed to write the stuff to disk, it wouldn't really write it to disk. And the same thing actually happens at the level of disk controllers too. So disk controllers typically have some sync operation, but they've got multiple levels of in-memory caching inside of them as well. And so you tell them to sync, and they'll eventually sync, but you can create these kind of weird corner cases where you do fsync, and the operating system will say, okay, and you pull the power out of the disk at just the right time, and in fact, you go look at the disk, and the thing it told you it had written isn't written. Okay? So getting this right, and again, this is something that's gotten better, I think, in a few years, but it's it's been hard. It's been a long battle. And then I guess the last one is just, I would say, performance issues. Like, the operating system doesn't understand as much about the semantics of the queries you're running as the database system does. So the operating system, for example, might apply this kind of sequential prefetching on files where the database system knows it's not going to be sequentially reading anything. So it's effectively wasting buffer space and wasting disk I/O by doing sequential prefetching. But it's applying this optimization because generally, if you don't know anything about the workload, this sequential prefetching can be a big one. Okay, so again, an example of a contention point. So anyway, it's been there's been a long-standing debate between these communities, and I think it's gotten better in the sort of last 5 years or so, where operating system people have realized that these database workloads are important. And the sort of popular operating systems like Linux now have hooks that allow you to do things like say, don't buffer this page, or they've improved the semantics of these sync operations so they really mean, write this page to this capsule. All right, any other questions? One more question?
Was there a period of time when databases moved after it?
Oh yeah. I mean, these database systems built in the 80s were all bare metal. They were built straight on, without an operating system at all, or with some very lightweight, thing that didn't, because they were the only thing running, right? And this still is the case that database servers are like basically you don't run anything else on your database server usually, right? So anyway, all right, that's all I have for today, guys. So we have a few minutes. If you are looking for a group or whatever, please do